Welcome to this lecture. In the last lecture, we were discussing how to develop the DFD model of any problem. We saw that developing the context diagram is extremely simple. We just draw a circle, write the name of the system in it, identify the external users or the external entities, and see what type of data they produce, they input to the system, and what type of data they consume, and that forms our context level diagram or the level 0 diagram. And then for the level 1 diagram, we just take up the SRS document and identify the functional requirements. If there is anything between 3 to 5 functions, then we directly represent them on the DFD diagram, level 1 diagram. But if there are large number of functions in the SRS document, very sophisticated system, then we need to group some of the functions into higher level functions, and normally in a good SRS document that is already done, that the functional requirement consists of subsections and each subsection contains several functionalities. So, we can represent those subsections in the level 1 diagram, and then we identify the data flows that occur among these functions, and then we do the decomposition to develop the still higher level diagrams, that is more detailed diagrams. And for decomposition, we need to take one bubble at a time and then see what are the sub functions, and we need to decompose between 3 to 5 sub functions in the next level diagram. And we were discussing that if there are too few bubbles in the next level, then the decomposition does not achieve anything. Let us say if there is one bubble in some diagram, some DFD, and in the next DFD again we give one bubble, then there is no decomposition. And even if we decompose one bubble into two bubble, then that is also not very meaningful. Typically, we need to decompose each bubble into 3, 5 or up to 7 bubbles. It should not be decomposed into too many bubbles, because that will make difficult to understand. So, the hierarchical nature will be lost and each level will become too much of details and it will become difficult to understand. So, at any level or any DFD diagram at any level, we should have about 7 maximum bubbles, and that will be a good DFD diagram. It will be easy to understand. Otherwise, if there are too many bubbles, then the diagram would become difficult for somebody to understand. We then keep on decomposing each bubble, take up one bubble in a diagram, decompose, and then again take up in those new decomposed diagram one bubble and go to decompose it in the next level, and so on. But to what extent we go on decomposing? We stop our decomposition when we find that it is decomposed to a function which can be described using a very simple algorithm, and its coding should not take more than few statements. Now, let us do one example problem, and normally when we learn anything, we start doing something very simple and then we do more sophisticated problems. The simplest problem that we do is called as the RMS calculating software. It is a rather trivial software which just reads a number, reads 3 numbers, between minus 1000 and plus 1000, computes their root mean square or RMS, and then displays the result. Very simple software. Now, let us try to do the context diagram. In the context diagram, as we said, we need to just draw a circle and represent the system, and we write the name of the system RMS software. Only at the context level a noun form of the process is allowed. In the other levels, we typically give a verb form to the process, and then it accepts 3 integers and produces the result, and we have the user for this. So, the same thing we have written it here in this slide. The name of the software is Compute RMS, and then there is this user who enters data items, and the data items are 3 integers, and it produces a result. So, this is our context diagram or the level 0 DFD. It is extremely simple to draw. Now, this is a very simple problem. It just consists of one function. Any decomposition of this into level 1, level 2 etcetera will become highly artificial, because this is a very simple problem. But then if we really want to decompose, we will see that for performing the RMS calculation, it first needs to read the numbers from the user, then do some validation that they are within minus 1000 to plus 1000, and then perform the computation root mean square and then display the result. So, these are the sub functions of the level 0 context diagram, because there is only one functionality. It is a very simple software. So, in the level 1 we decompose the function represented in the level 0, and then we can represent it in this form, that if read numbers, read the data items that are entered by the user. Just look at here that in the level 1 diagram we do not represent the external entities. The external entities are represented only in the context diagram or the level 0 diagram. The data items are entered into the read numbers, produces the validated numbers, it reads the numbers and inputs the number to validate numbers. It validates and then gives the valid numbers to this compute RMS. Otherwise, it produces an error message. The error message is given to the display bubble. Otherwise, it may give an RMS message, that is the result, and it produces that display. It may be an error or it may be the RMS. So, that is the level 1 diagram, but as I was saying that this is a highly simple problem, and therefore, a level 1 diagram becomes a very superfluous and very artificial. Nobody would really do a decomposition of a compute RMS. That is a very simple function by itself, and normally we would not decompose that, and in real problem modeling, DFD modeling, we do not decompose to this level, but just to give an illustration how decomposition can be done, explain that with the simplest example. So, I just mentioned here that we do not really decompose to this level. Compute RMS itself is a very simple function, and that can be represented, that can be coded using only very few instructions. Whenever we do a DFD model, a data dictionary must accompany it. The data dictionary lists all the data items that appear in the DFD and then write the meaning of that data item, and sometimes we might have to write a data item in terms of its component data. So, let me repeat that whenever we have a DFD model, we must have a data dictionary accompanying that. The data dictionary gives the meaning of all the data items that appear in the DFD. As I was saying that a DFD model can consist of a large number of DFDs, and all the data names appearing in all these various DFDs are listed in the data dictionary and their meaning is given. If it is a composite data item, it is expressed in terms of the simpler data items, but for the simplest data item we just write its purpose. So, that by looking at the data dictionary we should be clear about what are the meaning of the data that appear on various DFDs. The data dictionary is a very valuable document that is produced during structured analysis. The team members refer to the various data using the name and the decomposition given in the data dictionary. If we do not have a data dictionary, there is a chance of misuse. The team members may misunderstand the data that is represented on the DFD, and also while they refer to different data items, they may use inconsistent names and that will make it very confusing. So, the data dictionary standardizes the names of the data and explains their purpose and what they consist of. The complex data items consists of maybe some simpler data, it mentions them. For very simple systems, the data dictionary is quite manageable. If you have 10 or 20 data items, then you can just write down on a piece of paper or something and that will serve the purpose. But then in real projects, the data dictionary can have tens of thousands of entries, and if you start to manually write this, then it becomes very difficult. You may do mistakes or there can be redundant entries, and when you want to search the name of some data item, becomes very difficult to search it manually, and therefore, all DFD tools, structured analysis tools, they capture the data that appears in the DFD and build the data dictionary and maintain it in a relational database, so that query etc. becomes easy. So, all case tools help maintain the DFDs automatically, and they help to automatically search the data items. The case tools we will see that they can also answer query like which data item is affecting which processes. A process will affect which data items, where a specific data item is used, where it is assigned values, and so on. It becomes easy to answer this kind of question when these are maintained in an automated tool using a relational database system. Now, let us see the grammar by which these primitive items are combined into more complex data items. The rules are very simple, the symbols here. If we write a plus b, then we mean that A together with B. And if we write C is equal to A plus B, then C consists of A and B. If we use this square bracket, it means option. We write A comma B in square bracket, it means that either A or B. If we write A bracket B, then it represents that either A or A and B. If it is in curly bracket, then it represents repetition. If we write name 5, that means 5 data items, 5 name data items. If we write name star, it represents many name data items. Equal to is of course equivalence. So, A equal to B plus C means A consists of B and C. So, A is a composite data item containing B and C. As you can see that the data definition is very simple, using few operators like plus, square bracket, curly bracket and so on. And we can also write comments here within 2 stars. This is just one example here. A is a primitive data and we have written A is an integer. Numbers is a composite data, which is also a synonym is valid numbers, and it consists of 3 components A, B, C. Result is a data which sometimes can be RMS and other times it can be error. And RMS and error are primitive data item, and we have also mentioned here in comment the purpose for which that used. Error is used to represent a error message, RMS is used to represent the root mean square value. Now, if we practice a few examples, few more examples, we will see that given a new example we can easily draw the DFD model. But before we do that, let us look at another important concept in the DFD modeling called as balancing a DFD. Here we check if we decompose a DFD into a lower level DFD, then the data that is input, that is flowing in and out of the DFD matches the next level. What we mean here is that let us say we have a DFD model and we have some DFDs here. Now, let us say we decompose this bubble, take one bubble here and we decompose into a DFD diagram. So, we again let us say decompose into 3 bubbles this diagram, and it takes this data, produces a data, and this let us say finally produces a data, and this also produces a data. Now, let us say this takes A and produces B. Then in the next level we must also have A taken in here, and this let us say produces C and D. We must have B is equal to C plus D. This is balanced because this bubble here, the input is A, produces output is B, and when we have decomposed it into the next level, the data that is flowing into this diagram is B which is coming out from the diagram is C and D, and for balancing we see that the input is balanced, and for the output to be balanced C plus D must be equal to B. So, this rule of balancing is used at all decomposition levels. This is another example here, balancing. Let us say we have a level 1 DFD representation is this, that P 1, P 2, P 3 are 3 processes, and they are exchanging some data, and A is consumed by P 1, P 3 consumes C and E, sorry, the input to P 3 is C and P 3 produces D and E. Now, let us say in the next level we are decomposing this bubble here. So, this is the next level diagram, again decomposed into 3 bubbles. There are some data that are internally input across these different bubbles, but just see here that to this bubble C is input and this bubble outputs D and this outputs E. Now, we check here, yes, C is input here, D and E are output here, and therefore, it is a balanced decomposition. But let us say we had another input here, then that won't be balanced. Another concept is numbering DFD. So far, we saw that we just write the name of the process in the bubble, but if we write a number, that will help us in identifying the bubble. For example, if we write 0 is only for the context level, if we write the bubble 0, we can easily find out which bubble it is. In the next level, if we in the level 1 we write 0.1, 0.2, then by just looking at the number we would know which diagram, and that is the reason why the bubbles are normally numbered both by the tools and even if we are doing it manually. The context level is assigned a number 0, that is the convention, and at level 1 we decompose into a set of bubbles. Let us say we decompose into 3 bubbles, then we number them 0.1, 0.2, 0.3, meaning that the parent of this bubble is 0, that is context. And similarly, if we let us say find a bubble whose number is 0.2, 0.2.1, and then we know that the level 1 diagram, the second bubble, this is the parent of this, and for that the parent is the 0. So, this is a level 1 diagram, sorry, level 2 diagram, and so 0.1.2. So, this is a level 2 diagram. The parent of this diagram is 1, and for that this is the context diagram. Now, let us do one more problem, which is the tic-tac-toe game. Let us first understand the tic-tac-toe game. I think most are familiar with this kind of game. Here it is played between the computer and the user. Let us say the player marks, let us say by this red 0 and the computer makes let us say cross. So, the player mark is square here and then the computer will mark something. In response to that, the user will mark another square and so on. The player wins if we can occupy 3 consecutive elements in the row or column or on the diagonal. So, before the player can mark all along this diagonal, the computer has occupied this one, so that the player cannot win straight away. And if the game all the squares are over and no one has got any mark along a row or a column or a diagonal, then the game is considered draw. So, there are 9 places to fill and each player, that is the human player or the computer, they place their marks here. Now, can we draw the context level diagram of this? The game is intuitively clear and we are writing the software for this, and we want to draw the context level diagram for this problem. Please try this and we will discuss the solution in the next class. And as I was mentioning that if we can do few problems, we can develop the DFD model, then given even a very sophisticated problem, we can easily develop its DFD model. We will stop now, continue from this point in the next class. Thank you.